In this video here, we want to talk about the first derivative test. And in the previous lectures, or the lectures preceding this one, we started talking about intervals in which a function is increasing and decreasing. And so what we did was, if we look back for a second, what we noticed was we used critical numbers, right, to determine intervals for this. Well, what do we know about critical numbers, right? So critical numbers are where relative extrema occur. So we know relative extrema either means you have a relative max or relative min. So hopefully you kind of like see how this is all going together, right? Like functions are increasing or decreasing, and then maybe they change, maybe they don't change. I don't know, we'll see at these critical numbers. So this first derivative test here allows us to determine if we have a relative max or relative min based on that. So it goes like this. Let's let C be a critical number of a function f that is continuous on some open interval I containing C. If f is differentiable on the interval, except possibly at C, then f of C can be classified as follows. All right, so if f prime changes from negative to positive at C, so what that means, all right, if you're negative, that means you're decreasing. So the function negative means the function's going down. And then it changes to positive at C. Well, think about how you would draw that. You'd be at a valley, okay? Then f has a relative minimum at C, f of C. If f prime changes from positive to negative, well, think about what you have here. You have a peak, right? Because you're going from increasing to decreasing. Then f has a relative max at C, f of C. All right, if f prime is positive on both sides of C or negative on both sides of C, then f of C is neither a relative min or relative max. I'll show you some examples of that, or I'll show you some visuals of that. All right, so here's what we're talking about when you change from being negative to positive. Like you're decreasing. The critical value is 0, so you have a horizontal tangent line, and then you're increasing here. So whenever your intervals change from decreasing to increasing, you have a relative min. On a relative max, it's your interval is going to go from increasing, and then it's going to change to decreasing. Well, then that C right there is going to be a relative maximum, right? Because you're going to be at a peak. This is neither where it doesn't change. You can see here, it looks like it's about to change, but then it doesn't. Okay, this is going from increasing to increasing, or here it's decreasing to decreasing. So in those cases here, when it doesn't change, you neither have a relative min nor a relative max. All right, so here's what we're going to do in these examples. All right, we're going to put it all together here. All right, first thing we're going to do is we're going to find the critical numbers of any function. So we're going to start with the function, and the first thing we're going to do is we're going to find the critical numbers. Then what we're going to do is we're going to find the open intervals on which the function is increasing or decreasing, all right, using what we've learned in the previous two lectures. Then we're going to apply the first derivative test to identify all relative extrema. I'll show you how to do that in these two examples. And then finally, we're going to use a graphing utility to confirm your results. All right, so it's going to be a lot that's going on here. So here's going to be the first example. All right, so for this function here, f of x is equal to negative 8x cubed plus 24x minus 10. All right, the first thing I'm going to look at this, I'm going to say, okay, it's a polynomial function, so this domain here is negative infinity to infinity, right? Just the domain of this polynomial function. All right, so the first thing, boom, let's find the critical numbers. So you're going to have to find the derivative. This becomes minus 24x squared plus 24. So you're going to set that equal to 0 and you're going to solve it, right? So you're going to subtract 24 over. You're going to divide both sides by negative 24. And then when you take the square root to solve, you get two solutions, two critical numbers, okay? You get x is equal to plus or minus 1. All right, so we have two critical numbers here. Okay. So now what we're going to do is we're going to find the open intervals on which the function is increasing or decreasing. All right, so you're going to have to start at negative infinity here. Then you're going to go to -1. Then you're going to pick up at -1. And then you're going to go to 1. And then you're going to go 1 to infinity. All right, so then you're going to have to pick your test values. All right, so I'm just going to pick -2 here. I'll pick 0, and I'll pick 2, right? Pick it, between negative infinity and -1, I'll pick 2, right? That's -2, that's easy. Between -1 and 1, I'll pick 0. Between 1 and infinity, I'll pick 2. All right, then what you need to do is you need to find the signs, right? All right, so f prime of -2. All right, so just so we're clear, what is f prime? I'll rewrite it over here. F prime of x was -24x squared plus 24. Well, when you plug -2 in, you get 4. 4 times, 4 times -24 is -96 plus 24. Yeah, well, that's negative. F prime of 0, when you plug 0 in here, you're just left with 24. That's positive. And then f prime of 2, well, when you plug 2 in, it's the same thing as -2. You get 0. You get less than 0, excuse me. So conclusion. Okay, what's going on here? Well, look, from negative infinity to -1, the sign of the first derivative is negative, so it's decreasing. And then look, from -1 to 1, it's positive. Sign of the first derivative is positive, so it's increasing. And then from 1 to infinity, the sign of the first derivative is negative, so it's decreasing. Okay, so I found the intervals it's increasing and decreasing. Well, now look, how are you going to use your first derivative test, right? When the function, just to go back, when it goes from being negative, which is decreasing, to positive, which is increasing. Well, look, I was decreasing to increasing. So what do I have? I have a relative minimum. So here at -1, I have a relative min. But then look, what happens at 1? At x is equal to 1, what's going on here? All right? Well, it's going from, watch my pen, it's increasing, whoop, to decreasing. I have relative max. So that was just how you apply the first derivative. You see how the intervals are changing there. All right, so let me on the next slide, let me show you, just write it all out in a succinct conclusion here. All right, so this was our function. The function was decreasing on the intervals. It looks like it was decreasing. Was negative infinity to -1 and 1 to infinity. And then it was increasing on this -1 to 1. Then what we saw here is we have a relative min at x is equal to -1. So we have a relative min -1 comma f of -1. And just to save a little time, I believe when you plug in -1 into this, right, you get -24 plus 8 minus 10. So you'll end up getting -1, I believe, -36. And then it has relative max at 1 comma f of 1. Well, if you plug 1 in, right? If you plug, f of 1, you get -8 minus 10 is -18 plus 24. So you get at 1 comma 6. And look, let's use our our graphing calculator here just to verify the results and see if we did it right, just to make sure. So this is going to be negative 8x cubed plus 24x minus 10. And let's take a look. Let me zoom out. Yeah, it looks like we got it. Like it looks coming down. We have the relative min here, relative max here, and we got it. Looks good. Looks roughly what it should be. All right, let's do a trig one now. Okay. And I put the unit circle here for reference. All right, let's look at f of x is equal to x minus 2 cosine of x. And let's just look on the interval from 0 to 2 pi. All right. Got to find the derivative. F prime of x. Well, that's 1 minus 2, and then this is minus sine of x. So this ends up being 1 plus 2 sine of x. Well, what you're going to do is you're going to set this equal to 0 and solve. Okay, so you're going to do 1 plus 2 sine of x is equal to 0. So 2 sine of x is equal to negative 1. Or you're going to look when sine of x is equal to negative 1/2. And that's why it helps to have this, unit circle here if you forget, right? So like the sine is the y value here. So it looks like this happens at 7 pi over 6. And then the other one is 11 pi over 6. Okay, so I got the endpoints and I've got the two critical numbers here. All right, so again, all I'm going to do is I'm going to take this and I'm going to carve up the interval and do the same exact procedure. Yeah, I'll do it on this slide right here. So interval. It looks like we have the interval. It goes from 0 to 7 pi over 6. And then it's going to go from 7 pi over 6 to 11 pi over 6. And then from there, it's going to go from 11 pi over 6 to 2 pi. Are you going to need your test value? Well, so look, you can pick any number between 0 and 7 pi over 6. I'm going to pick pi. It's easy here. Between 7 pi over 6 and 11 pi over 6, I'm going to pick 3 pi over 2. And then this is a little confusing. So I got to pick a number that's between 11 pi over 6 and 2 pi over 6. So what I end up picking is 13 pi over 7. Okay. So there's like a trick here, like what number is just above this, that you could plug in that's really easy. Well, if you double if you double 6, you get 12, and 12 minus 1 is 11. So if you pick 7 times 2 is 14, minus 1 gets you 13. That number is going to be closer, larger than this one. All right, so let's look at sine of first derivative. All right, so we're going to look at f prime evaluated at pi. Right, so like this is our derivative. Well, what is sine of pi? It's 0, right? So that's easy. So this is positive. It's just 1. F prime of 3 pi over 2. Well, sine of 3 pi over 2 is negative 1. So this is 1 plus, 2 times negative 1. That's negative. And then f prime of 13 pi over 7. That one you can use a calculator for. And if you plug it into this, it ends up just being greater than 0. Okay, this ends up being like negative 4 point something times 2. So it's not greater than 1. Okay, so our conclusion here it's increasing on this interval, decreasing on this interval, and then it's increasing on this interval. And you can see where it changes, right? So it's going to go increasing to decreasing, boom, boom, boom. That's going to be a relative max. And then it's decreasing to increasing. That's going to be a relative min. All right, so let's go back to let me sum this all up on the next slide for all of this. Okay, so our original function was x minus 2 cosine of x. So let's see where it was decreasing. Well, it looks like it's decreasing just from 7 pi over 6 to 11 pi over 6. And then it was increasing on, it looks like 0 to 7 pi over 6 and 11 pi over 6 to 2 pi. Okay. And now look, we saw that it had a relative max at the point, it changes at 7 pi over 6. So that's at the point 7 pi over 6 comma f of 7 pi over 6. And if it helps at this point just to see what f of 7 pi over 6 is, well, you're plugging in for x, so that's 7 pi over 6 minus 2 times cosine of 7 pi over 6. So cosine of 7 pi over 6 is this, minus the square root of 3 over 2. So you know, negative negative would make that a positive. And then we have a relative min at, well look, it's decreasing and then it's increasing. Changes decreasing to increasing. So that happens at 11 pi over 6 is where that change occurs. And then just to see it, f of 11 pi over 6, plugging in gets you 11 pi over 6 minus 2 times cosine of 11 pi over 6 is just square root of 3 over 2. All right, and in both those cases, you could cancel the 2's out. But this is that process. So it's a lot of that increasing and decreasing. It's just with that extra part at the end where you look to see where does it change from increasing to decreasing. Increasing to decreasing means you got a relative max. Decreasing, increasing tells you have a relative min. All right, class, as always, if you have any questions, just let me know. Oh, and before I end, if you plug this into a graphing utility, you'll be able to verify that. But we'll skip that for this one.